Hello, everyone. I'm Bala from Budapest University of Technology and Economics, Hungary, and I'm presenting the paper called Combining Packet Programs to Reconfigurable Switches, Theory and Algorithms. My co-authors are Erika, Costin, Raiciu, and Gábor Rétvári. I'm really glad to have these guys on board. Besides our universities, Ericsson also backed our research. So let's jump into it. As you all know, programming reconfigurable switch pipelines using a high-level domain-specific language like P4 is increasingly adopted. Applications are booming in size, data plane programs are growing in complexity, new programmable switch ASICs on the hardware side have more data plane resources and more pipeline stages. We can feel that it raises some algorithmic issues. So let's define this problem a little bit better. So the data plane programming is a top-down approach. The required behavior of the network is described in a declarative P4 program that is mapped down to the hardware by a compiler. And this compiler must analyze the P4 program given an abstract model of the hardware, which includes limits of memory space, width, or types, number of processing stages, maximum level of concurrency at each stage, and so on. And the compiler has to find the best encoding such that all the constraints are met. Here, the best means the one with minimum number of stages, minimum power, etc. So we call this problem the pipeline embedding problem. So the stage was set for this problem by a paper some years ago called Combining Packet Programs to Reconfigurable Switches, and it proposed an abstract model for pipeline embedding with ILP and heuristic algorithms solving it. Some issues remained open though. For example, the ILP possibly runs for exponential time. It runs hours for a moderate sized pipeline, as we also measured. And on the heuristic side, they didn't prove any guarantees of goodness. I mean, if the results are close to the optimal solutions. So unfolding the algorithmic landscape of this pipeline embedding problem was required. So what are our models? A bit more detailed. The control flow dependencies of a P4 program are represented by a directed acyclic graph, a DAG, which is called the table dependency graph, TDG. And its vertices are logical match action tables, and the arcs are dependencies between these match action tables met. The packet processing pipeline, on the other hand, is modeled here as a directed path with nodes representing the pipeline stages and the arcs encoding the succession. For simplicity, we say that the switch has infinitely many stages, so that the objective is to minimize the number of stages in the embedding. Here's a schematic map of a switch. A packet comes, it gets parsed. It goes into the first stage, which has TCANs and SRAMs. It goes through the stages, a number of N stages, and after the parsing, it leaves the switch. So a full model of the hardware is very complex. So we decided to make some simplifications, gain some insight on it, and then gradually we put back the constraints and reanalyze the problems. So we ended up with a bunch of models. The simplest one is called InfCap, where the switch was modeled by a directed path of stages, each with infinite capacities, and we took in account only the mapping concurrency due to dependency between the tables, so that no nodes on the two ends of an arc of the TDG could be mapped to the same stage. They have to be mapped on different stages. Then we put back the one-dimensional capacity demands, so the number of entries of each tables were took in count. Then we enabled tables to be split between stages. For example, a large IP routing table, sometimes it doesn't fit to a single stage, so we have to divide it in multiple stages. Then we took in consideration the width of the table entries. So we have two-dimensional capacities and demands. And then we said that we have two kinds of resources per stage, both decans and SRAMs. And then we limited the maximum number of tables per stage, which is also a common constraint. Our final model is a full-blown pizza model with crossbar constraints, work packing, and etc., as also described in the former paper. So what are our results? The simplest model can be solved actually in linear time optimally, but even putting simple capacity constraints back, the problem becomes NP complete. This is simply because these problems contain some NP hard problems as special cases. So we have more bad news to come. All these versions of problems we provided, so they do not have polynomial time approximation schemes. So there is no polynomial algorithm which can yield a solution with arbitrarily small multiplicative error compared to the optimal solution, unless P equals NP. Bird's view for these proofs is just showing that we have an instance family such that we can embed each instance in k stages exactly if a related NP hard problem has a solution. Otherwise, we need k+1 stages. So it yields an inapproximability better than a factor of k+1/k. For example, if we have one-dimensional capacities, we take a TDG with no arcs, such that the total size of nodes of the TDG is 2 times the size of the stages. This means that we can embed the TDG in 2 stages exactly if the partition problem has a solution over the table sizes, which is NP hard to decide. We have good news on the bright side. We have constant approximations in quasi-linear time on all of these problems. Here are our worst case constants for these approximations. The idea is that we call it the first fit by level and size, that we group the TDG nodes by their level. Here, a node V is on level I if the longest directed path from the root to V has a length of I. For example, L is here on level 3, and it would be on level 3 also if there would be a direct link from R to L, because the longest path from R to L has a length of 3. Okay, so what these levels know that the nodes in each level, the tables in each level, can be mapped into the same stage. So for each level, we can apply some kind of bin packing heuristics, or when we have multiple resources available, then we have to combine bin packing. So that's why we have higher approximation constraints here. What is the takeaway? Pipeline embedding is NP hard. And also inapproximable with arbitrarily small multiplicative factor in polynomial time. And on the bright side, it is constant approximable in quasi-linear time. We want to investigate in the future the optimality gaps of Chipmunk, Domino, and other compilers, and also that the question of how to write better P4 programs. Thank you for your attention. I'm happy to take questions. I try to answer them. Thank you.